Hi, today I'm going to talk about scalable AI development for instruction tuning, and I'm going to go over a case study that the research group developed over the summer on the RedPajama suite of large language models. So I want to begin with the summary. Large language models require fine-tuning the human input in order to be useful. And a part of our hypothesis is that this will extend to business use cases and subject matter experts. And in fact, they'll be even more applicable to business use cases than they are to the general public. So at Snorkel, we've been enabling the fine-tuning process with efficient, scalable methods that keep humans in the loop. I'll unpack that a little more in the next few slides. And we'll go over a case study, the RedPajama suite of large language models that actually illustrates the power of this method. So I'm just going to go over some basics. You may have heard some of this already at the summit, but I want to set the stage for what we're going to present. So large language model development involves three basic stages. So there's the pre-training of base models. Base models are pre-trained on tons of scraped data, often trillions of tokens. When you put them into action and you prompt them to do things for you, the responses tend to be grammatically correct and on topic. But they can often be way off. They don't get the details of the prompt that you're trying to give them. They often also lack domain-specific knowledge, especially if it wasn't in the scraped data, which is going to be especially relevant to businesses that may have proprietary data that hasn't been scraped for said base model. Once a base model has been pre-trained, that therefore requires a fine-tuning process in which these models are retrained to specific data sets that contain the information relevant to however that large language models can be used in the future. And there are two basic kinds. Again, this is kind of a cartoon version, but going over some really some basics. Instruction tuning involves data sets with crafted instruction response pairs that illustrate the kinds of things that you want this large language model to do for you in an application. There's another technique called reinforcement learning with human feedback, not as used as commonly. It's a very model-intensive process, but it's one in which you generate data sets of human preferences and rankings of responses from existing large language models, and then you use that signal, that human preference data, to fine-tune the model. In all of these processes, quality data is key. So garbage in, garbage out. That's been true since the beginning of machine learning. It's arguably even truer here for large language model development. Once you fine-tune your model, you put them into play. We can call this kind of the application phase. And there are a lot of technical details that go into applications, such as good prompt engineering, something called in-context learning, in which you give kind of demonstrations of what you want the model to do without necessarily fine-tuning it, guardrails that prevent things like hate speech, and a really interesting technique called retrieval augmentation, in which the model can actually retrieve a document from a business data lake, for example, and ask questions and answer questions from that document. We won't talk a lot about the application stuff today. I wanted to mention that, though, because at the end of the day, we actually need to use these models for real life. And so we've been doing a lot of focus in the fine-tuning phase. We're beginning to do a lot more research on the application phase, especially retrieval augmentation. In the future, we plan to also tackle pre-training. But today, I'm going to talk mostly about the fine-tuning piece, tackling all fronts, but we began with a focus on fine-tuning. So if I were giving this talk a year ago, I likely would be looking at the left-hand side of this slide and talking about how fine-tuning requires golden data generated by experts or humans that are kind of good at writing out responses to train the data on. Often these experts, in order to be effective at producing this training data, require a lot of management. They often need to be paid well enough to be incentivized to do a good job. And it can take a long time for them to generate these responses. So if, for example, you're training a large language model to write essays for you, you need to train it on data with well-written essays. And as anybody remembers from high school and their college days, writing a really good essay can actually take a long time. So I think that the instinct here is that we have scalability issues when it comes to quality, not necessarily in terms of volume of data, because you can fine-tune these models. You can get away with a small amount of data, like hundreds, thousands of examples. They all have to be really good examples. And so there's a scalability issue with respect to human hours. the time being spent, and also the pure resources that need to be brought to bear in these problems. If you read some of these original papers on large language model fine tuning, companies such as Anthropic and OpenAI put a lot of work into the human piece when it came to building out these training data sets. So for a business, that can be daunting because they are not necessarily equipped to put the same number of resources into that work. So there's a scalability issue that remains, not necessarily with respect to number of examples, but with respect to quality. So a lot of the technical developments that I've seen over the past 6 to 9 months have been focused on solving scalability issues by kind of automating as much of this process as possible, and not using humans, but using existing large language models to actually generate those responses or ranking. So kind of taking the human out of the loop so people don't have to devote all of these resources to the fine-tuning process. At Snorkel, we continue to operate from the insight that at the end of the day, only humans and subject matter experts can actually define what good looks like. Models such as ChatGPT have indeed provided some impressive results on being able to rank responses, for example, or generate things that are high quality. Those are typically in kind of these generalist contexts in which you're asking it to produce data that is kind of with everyday use, not necessarily kind of specialized data. And in fact, when we've tried out some of these automated methods with more specialized use cases, these same large language models won't do as good a job. So part of the takeaway here is that in order to effectively fine-tune models, we need to keep subject matter experts and humans in the loop, because at the end of the day, we're the ones who know what good looks like. We can't expect existing large language models to do all of that work for us. And if there's a business use case, for example, that requires specialization, we, at the end of the day, need to bring these business SMEs to bear on the problem somehow. Maybe we don't want to, use them to write out 1,000 different examples for us because that's not, cost effective. We do need to find a way to keep them in the loop. So the way we're tackling this scalability issue is by indeed keeping subject matter experts, keeping humans in the loop of generative AI development, but maximizing the value of their time being spent. And the way we're approaching this is by building what I'll call these kind of guiding models that allow them to more efficiently direct the training data development process and provide signal that then the large language models can learn from kind of more efficiently. And today I'm going to talk about 2 such guiding models. One is instruction classification. So again, we have these instruction response pairs we want to fine tune to. So it's all about instruction tuning, fine tuning on instruction response pairs. First, we want to classify the instructions. We want to know what we're feeding the model, make sure it's representative of the task we'll want this model to do in the future. All right, that's model 1. Model 2 is response quality. We want to make sure that the way large language models respond are of high quality, which in turn requires that in the training data, those responses are of high quality. So 2 models, instruction classification, response quality. So let's get into the case study. I'm going to talk about the RedPajama suite of large language models. This is a suite of, quote, generalist models that are trained on a wide variety of kind of everyday tasks developed by a sister startup, Together.ai. It was pre-trained on the same data set used for the Llama model developed by Meta. And the goal of the project was to help Together improve its instruction tuning process with higher quality data sets. The original data sets came from 2 sources. One was the Open Assistant data set generated by kind of a volunteer-led effort. I won't get into a lot of details, but there was instructions and responses that volunteers were able to contribute, tasks they thought would be good for a large language model to be able to solve for, as well as responses. They would sometimes rank these responses as well. The second data set was actually provided by Databricks, also open source. It's what Databricks used to develop their DALL-E 2.0 model, large language model. And that data set came from employees within the company. As I said earlier, there are 2 basic models we brought to bear on these kinds of problems. One is classifying instructions, the other is quality. And so to that end, we first began with an instruction classification model. So we used a technique called weak supervision to classify instructions. Just briefly, weak supervision is a technique pioneered at the company in which you can write kind of, quote, programmatic labels, kind of heuristics or rules of thumb that can automatically generate data for you. Sometimes these rules of thumb will conflict with each other, but if you write enough of them and aggregate them with model efficient methods, you can produce these training sets that are almost as good as what a cohort of subject matter experts would produce. So the idea is you write these programmatic labels, and I'll show examples of those in a few slides, rather than individually labeling each instruction as to what kind of class it was. And I'll go into the kinds of categories we use in a few slides as well. So model 1 was instruction categories. Model 2, define what good looks like for each category. So this kind of quality model. And then step 3, fine tune on a high quality data set that was both curated and representative with respect to instructions. Again, I'll go into details later, but the bottom line is that we were able to use this process, and in only about 1 to 2 days of programmatic data development resulted in a much higher quality data set. And in fact, we got a 9-point lift on what we'll call win rate of the data against ChatGPT. Again, I'll do some more details, but that was the bottom line. We went through this 3-step process and was very quickly able to achieve something. And I'm emphasizing the quickness of this process because part of the proof of concept here is that we're solving for scalability. We didn't have to spend days or weeks generating data. This took 1 day of work. All right, let's unpack step 1 a little more. This instruction classification model, again, was built to ensure representative training data. We used instruction classes that were rooted in prior work by companies that had pioneered large language models, including Anthropic and OpenAI. We had 2 question answering instructions, one without context, just a simple question like, when was Google founded, without any additional information. Closed QA, closed question answering, in which you provided a document and it has to answer a question based on what it was provided. Brainstorming tasks like, give me ideas for planning a beach trip, or making more money. Generation tasks such as drafting documents, and then summarization, in which you actually take whole documents and you summarize them, which is a very common kind of task, especially in businesses from what we've seen. And what I'm showing on the right-hand side is just an example of one of those heuristics or programmatic labels that we use to classify. So we use something called a regular expression, and said if you see the beginning of the instruction having the words please and then a generate or make plus some other logic, classify it as a generation class. Step 2, build a response quality model. So here we defined these heuristics, these programmatic labels, based on a wide variety of features. We use something called perplexity, which is a way of measuring the overall kind of chattiness of the response, even the instruction if you want. Simple features like the duration of the response, indicators of uncertainty. So for example, if the response begins with something like, I don't know, we want to rank it as low quality because we know it's not going to answer the question. Instruction response similarity. So this was what's called a cosine similarity in an embedding space. Can talk about that on a more technical level for anybody who's interested during QA or offline. Wide variety of labels or of features that we use to define these programmatic labels. Importantly, a lot of these labels capture dependencies on instruction class. So for example, some of the question answering type tasks required shorter responses. They didn't need to be long essays if you're just looking for a date, for example. Brainstorming tasks, on the other hand, people seem to prefer longer responses in list form. In generation tasks, especially longer and chattier. The lower quality data we saw involved shorter responses in the generation tasks. And it looked like the people writing out these answers were just trying to get it over with. So what I'm showing on the right-hand side here is actually an example of a programmatic label that we generated to capture some of these intuitions. So, if the instruction class is brainstorming or generation, and the instruction involves something involving a list. On the lower hand here, we have, let's use a regular expression to look for lists in the response. And if it's a list, let's call that high quality. And again, this isn't our only definition of high quality. This is being combined with a lot of other heuristics to approximate a good training set that an SME would develop to define a high quality model. So how do we know if we're doing a good job with this response quality model? Let me talk for a minute about win rates. It's actually a pretty standard approach for judging the quality of the output of large language model. It's basically the percentage of the time a person or some other model prefers the output of the generative AI to some baseline. And it can be used to track quality model performance. And for example, if a large language model has a higher win rate over 50% versus some baseline like ChatGPT, we call that higher quality, and then the goal is to increase that win rate. It's a way of tracking something without necessarily having to make assumptions about what quality looks like on some more absolute scale. And we evaluated the response quality model using these win rates initially by plotting human win rate over ChatGPT. So we actually had labelers on a small set. We asked them in a double-blind experiment whether they preferred dataset responses to what was produced by ChatGPT, and then we asked, could our response quality model predict whether the data was preferred over ChatGPT or not? That was our basic measure. And importantly, what we could do then is use these win rates to do a novel kind of error mode analysis. So for example, if there are areas where the response quality model fails to predict preference, let's write some more labeling functions, more programmatic labels to tackle that error mode and ensure that the model can predict what was preferred in the future, in a future iteration of that model. So once we had this quality model up to sufficient performance using this win rate analysis, we actually used it to curate. As you may recall, we developed this instruction classification model to actually classify instructions. And what we did is we measured the distribution of instructions as a function of quality threshold. So threshold simply being how good does the curating or quality model need to think the sample is in order to include it in a curated version of the data set. The higher that threshold, the smaller the data set, and the greater the risk of it's not being as diverse. What I'm showing here in this table is what we use to determine that threshold of quality for curating the data set. And this middle column, this measure of entropy, was our way of tracking the distribution diversity. And what we found was that as we increased threshold, we saw a decrease in diversity at the very end. We ended up choosing at the very highest kind of quality threshold. We ended up using kind of a middle ground that ensured actually higher representativeness than the original curated data set, but with a projected win rate against ChatGPT that was pretty high compared to baseline. So this is how we used, these are kind of the parameters we used to actually curate the data set with the tools we had built. And what we found was that after curating, we ran an experiment in which we asked people in a kind of double-blind fashion to ask whether we asked them to judge whether they preferred the responses in the data set over ChatGPT. And what we found was that when we use a curated data set, the win rate increased by 9 points, and that the increase was consistent across instruction classes. So this was key. If we had found a huge lift in just one instruction class, we would not have really solved the problem. What we wanted to see was an improvement across all instruction classes. As you may observe here in the table, there were some where the win rate against ChatGPT originally was very low. Only 30% of the time were the brainstorming responses preferred the ChatGPT. When we curated, we increased that by 10% or by 10 points. We then went ahead and said, okay, well, the goal here is to fine tune on something that's higher quality and ensure that that large language model is producing higher quality responses. So then we went ahead, we fine-tuned RedPajama on the curated data set, compared that with the uncurated data set, went back to the same group of humans who did that double-blind experiment, and we asked, well, which do you prefer? The RedPajama version trained on the curated data set or the one trained on the uncurated data set? And indeed, what we found was that they preferred the one trained on the curated data set. We got about an average of 6 to 7 points of lift across instruction classes. And importantly, that was also consistent. So we weren't just getting a huge gain in one thin data slice. It was a broad-based increase in quality, not just of the data set, but of the resulting large language model. We also went in and asked, well, okay, where are we seeing the biggest lift? Can we get some more insight into why this works so well with just 1 to 2 days of work? And we hypothesized that we would see it in areas that align the most with these heuristics we had written. And in fact, as you may recall, we had instructed this quality detection model to look for longer, chattier responses for generation tasks. So we went in and we said, okay, what are some generation tasks that might actually show this? And we went in and we saw that there were a lot of instructions about emails and kind of drafting documents. What I'm showing here is one about an email. And we found that in that data slice, when the instruction involves generating email, we saw a 12-point lift from the large language model, twice the rate of some of the other tasks. And I'm just showing an example of this down here, randomly picked from the email data set. The version 1.5 response for the curated data was complete. It's kind of a sane response. The instruction was just draft an email complaining to a shop about something that broke. The version 1 response that had been trained on the uncurated data didn't even complete. It started, you could tell it was on topic, but it wasn't even a complete response. So just an example of what we get from training on higher quality data. So let's wrap this up, and I want to repeat some of the takeaways here. Large language models require fine-tuning the human input in order to be useful. Our hypothesis is that this extends the business use cases and subject matter experts. We're actually beginning to replicate these results in other projects, including ones involving customers and prospective customers, so more specialist models. And what we're showing, both in this use case as well as the ones we're exploring with our customers, is that we're able to provide efficient, scalable methods for instruction tuning that keep humans in the loop with really a fraction of the time that would otherwise be required of these subject matter experts. I showed that to you in this open source case study, the RedPajama suite of large language models, in which we obtained 9-point lift in data set quality with only 1 day of work. And as I said, we're replicating these results. So that's it. Anybody who has questions, who wants to discuss with me offline, please feel free to reach out to me. Here's my email. This is all very exciting work. It's really the field is evolving rapidly, and we're very excited to be able to contribute to really efficient development of these models that keep humans in the loop. Any ideas, any other questions, please shoot them to me towards email. Thanks again.